Okay, so today we went over our practice and the homework we did. I want to make sure that you get the next group of notes. So these notes are for Monday. Remember electron configuration for ions. Positive ions, which we call cations, have lost electrons. These electrons will be lost from the highest energy level. Then we have negative ions, which are called anions. They have gained electrons. These electrons will be added to the highest energy level. So let's practice writing longhand configuration for the element and the ion. Sodium. So sodium is here in 3s1. So 1s2, 2s2, 2p6, 3s1. This is an alkali metal, and we in group 1a, and we know that the alkali metals are cations. They have a +1 charge, so the sodium ion will lose this 3s1. It will donate it. So 1s2, 2s2, 2p6. So this is the ion for sodium. Okay, looking at cobalt. Cobalt's a transition metal here. Okay, we know that it has this 4s, so it has a +2 charge. So cobalt is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d, 1, 2, 3, 4, 5, 6, 7. Okay, so cobalt ion +2. It's going to lose this 4s. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d7 because it loses this s2. Okay, so our steps to writing this configuration, I guess I should have written that earlier. We did write them today. Number 1, we're going to find the element. Number 2, we determine the configuration and look what family it's in. And number 3, look or what ion. I'm sorry, look what is the highest energy at the highest energy level. Highest S or P. Okay? Alright, so on to the next page. Okay, so you practice oxygen and oxygen ion. I want you to pause the video to do that. So I'm going to continue. Oxygen is 1s2, 2s2, and 2p4. So our oxygen ion, this is going to be an anion in group 6a, so it has a -2 charge. It's going to gain 2 electrons. So 1s2, 2s2, and 2p6 because it gains those 2 electrons. So 4 plus 2 equals 6. Then niobium, Nb. Okay, so niobium, let's look at the longhand is going to end up in 4d3. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and then 4d3. So it tells me right here that it loses 3 electrons, and so it's going to lose this 5s2, and then the next energy level after that will be the 4d3. So we're going to 2 minus 2, and then 3 minus 1 for the niobium ion. So it will 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. We're going to skip this. We no longer have the 5s, and we go straight to 4d2 because 3 minus 1 is 2. Pause that video and rewind it if you need to. Okay, isoelectronic. Iso, here's that prefix again, iso meaning the same. Huh? I sure did. Never. Yeah, here, let me have them. I have a big old container over here. All right. Drawer for it.
By the end of the year, there has to be 12 picks.
Oh, yeah, that's because I'll have gone and bought them. Okay. So iso, meaning the same. Electron configurations end up being exactly alike. They ultimately have the same number of electrons. So, for instance, an ion and a noble gas. Let's look at that. And let's look at that example. Chlorine. Chlorine we know is an anion and has a -1 charge, so it's going to gain 1 electron. So let's write that noble gas. Let's write that configuration down. 1s2, 2s2, 2p6, 3s2, and 3p5 plus 1 equals 6. So it'll be 3p6. Oh, I'm sorry, I wrote a spot here to write that down. 1s2, 2s2, 2p6, 3s2, and then 3p6. So let me go back and fix that. Because that should be 3p5. And then we're going to gain 1 electron and be 3p6. So we can see that argon is 1s2, 2s2, 2p6, 3s2, and then 3p6. 3p6. So when chlorine adds 1 electron, it becomes like argon. So this should be a 5. So one example is an ion and a noble gas. The second example is an ion and another ion. Okay. So phosphorus and a phosphorus ion. So phosphorus is here at 3p3, 1s2, 2s2, 2p6, 3s2, and 3p3. Phosphorus is in group 5a, so it ends up gaining 3 electrons. 1s2, 2s2, 2p6, 3s2, and then 3 plus 3 is 6. So then let's look at calcium. Calcium is in 4s2. It's an alkali earth metal. 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. It's a +2 ion, so that means it's going to lose the electrons to this at this higher level. 1s2, 2s2, 2p6, 3s2, and then 3p6, because that goes away. Now it says the phosphorus ion and the calcium ion are isoelectronic because they both have, let's count them, 2, 4, 10, 12, 18 electrons. Okay, so what are 5 ions that will be isoelectronic with xenon? So here's xenon. Well, iodine -1 would be 1. And if you want to pause this video and see if you can figure it out for yourself, that'd be great. Te -2, Sb -3, and so all of these are in energy level 5, so the cations from energy level 6. So cesium +1 and radon +2. All right, the last thing I'm going to talk about right now is the valence electron configuration for a family. the valence electron configuration for a family, all members of a will have the same valence electrons. And we look for those by the A at the top. These configurations will not include an energy level. I'm only going to ask you about those in the representative elements. So, we know that everything, this group here is the alkali metals, and they are in the S1. Whoops, I meant to put that as a superscript. S1. So this would be an S1. The alkali metals, earth metals, are S2. So these are the alkaline earth metals. Okay. Then the carbon, or the next family is the boron family. And the boron family is going to be S2P1. The carbon family is S2P2, because here's the S's and here's P1, P2, P3, P4, P5, and P6. So S2P3 for the carbon family, for the nitrogen family. The oxygen family, S2P4. The halogens, S2P5. And the noble gases are S2P6, with the exception of helium, which is just S2. So remember that this is the boron group, the carbon, the nitrogen, the oxygen, the halogens, and then the noble gases. Okay, so now I want you to practice. What is the valence electron configuration for the boron family? S2P1. The noble gases are S2P2. The halogens are, S2P6 for the noble gases. 6 minus 1 is the halogens, S2P5. Alkaline earth metals are straight S2, with the exception of helium. Carbon family, S2P2. Oxygen family, S2P4. Alkali metals, S1. And last, the nitrogen group, S2P3. Okay, make sure that you have gotten that done. We'll do the ground state electron and orbital diagrams last.